Welcome back. So today we're going to talk about a new model for parallel computing, which has become quite popular in recent years. And this is the Mapreduce model. So to start out, let me give some background about the motivation for Mapreduce. So you can think of Mapreduce as a parallel programming model that's focused more on data than computation. And also, it's very focused on achieving low cost and high scalability. So basically, Mapreduce was motivated by the explosion of the internet about 20 years ago. And so the types of data that Mapreduce is intended to process, a lot of that comes from the internet, and also from the data that users of the internet generate. Okay, so this includes things like web pages themselves. Right. It also includes information about users of these web pages. It includes image data, video data that are produced. But in addition to this, you can also use Mapreduce for other types of data processing. So for example, for traditional scientific computations of, let's say, physical data or biological data. Okay, and so the idea for processing all this data is this sort of new method for doing science that's been proposed in recent years, which is the so-called fourth paradigm of science, where supposedly if you want to solve a scientific problem or even some sort of financial or social problem, if you're talking about the internet or things like that, right? You're going to so the traditional way of solving these problems was to collect, let's say, a small bit of data, right? And then using that data, you're going to generate a bunch of hypotheses, and then you're going to construct sophisticated models of how your system operates based on these hypotheses and the limited data that you have. And then after that, you're going to go validate your model by collecting some more data. Okay, so it's driven primarily by the model construction step, right? Of course, you need the data to guide your model construction. But the heart of the traditional way of doing science was to construct these models. Right? And this is a manual process which is done by scientists and which is done by thinking very hard about your problem and trying to get some insights. Okay, well, the new way of doing science, the so-called data science method of doing science, is to just basically ignore the model construction step and to just collect as much data as possible. Right? And then throw all that data into some sort of algorithm, and you want just the algorithm to look for any patterns that it can find. Right? And then so the algorithm spits out a bunch of patterns that it detected, and then somebody else is going to go through these patterns and then maybe throw away the unreasonable ones. And then so for the patterns that they keep, right, hopefully one of them is actually the correct answer for your problem. Right? Hopefully that gives you a way to model your problem and to solve your problem. Okay, so it's almost like if Newton wanted to discover his laws of gravity and laws of motion, right? So instead of sort of thinking about this problem and making some observations and trying to validate his theories with the observations, right? Instead, suppose that Newton just took a million things and then put motion sensors on these things, okay? And then he just collected huge amounts of data, and then from that data, he throws all that data into a machine learning algorithm, and then out comes a bunch of possible theories for how objects move, right? And then he somehow goes through all of these theories and then filters out the completely non-realistic ones, and then what's left is hopefully his actual theories of motion. Okay, so that would be how this so-called data science paradigm would try to solve scientific problems. Okay, so you can argue whether this is a good approach or not, but this seems to be the main approach that people are taking, especially towards processing these sort of sort of not really scientific types of data, like sort of web data and user data. We don't really have any good scientific theories for how people behave, and so basically all you can do in that circumstance is perhaps construct these sort of statistical and these these data-driven type of models for user behavior. Okay. So anyways, so that is the sort of the basic setting from which Mapreduce, this framework of Mapreduce, arose. Okay, now the other aspect to Mapreduce is that they're very focused on cost and scale. Okay, so in fact, Mapreduce, when you build a Mapreduce system, you want to make it very cheap, but you want to have lots of computing power within that system. And so the way to do that is to scale the system out instead of scaling it up. Okay, so what that means is when you scale out, you're just going to buy a lot of computers. And they can be like, pretty cheap computers. Okay, so they're not very powerful computers. And then you're going to connect them through some sort of communication network. But that network itself can also be quite, not very powerful. Just some sort of cheap, simple network. Okay, but just the fact that you have, thousands or tens of thousands of these computers, gives you a lot of computing power. Okay, of course, you can't do too much communication between these computers because your network is very is rather weak. But if you have a problem which is not very communication intensive, then you can actually solve that reasonably efficiently on this computer. And all of this is very cheap because you can just buy cheap computers and cheap networking, and then and all of this is sort of commodity, right? You can just go to a store and buy this stuff. Okay, as opposed to designing. So the other way of building a very powerful computer would be to scale up the computer. Okay, so scale up the computer means that you design very high quality components, right? So for example, you have very fast processors. You have a fast interconnect between the processors. Okay, so that would be like a supercomputer, right? Whereas the scale out approach would be like a data center. Okay, so Mapreduce was designed for data centers as opposed to supercomputers. Okay, so so Mapreduce ties in very well with cloud computing, right? Which of course is being done on data centers. Okay, and then so these clouds are basically thousands and thousands of these commodity processors, which are tied together by some sort of simple networking. Okay, and then the Mapreduce can it will create many jobs, and it will manage how it will schedule these jobs on all of these different computers. Okay, so Mapreduce originally was developed by Google. Okay, and they were trying to solve pretty simple problems back then. So in fact, it was intended just to solve some sort of text processing problems. Okay, some very simple text processing problems. And so they just sort of coded up a system to solve this problem. Okay, and somehow the system sort of grew in popularity. I guess because people found that many of the problems that you need to deal with in the internet setting. Okay, so if you're running some sort of internet company, many of the problems that you're trying to solve are not very complicated, but they require large scale because you have huge amounts of this data. Okay, so for example, you could have user logs. Okay, so you want to make sure that your users keep coming to your website. Okay, so in that case, all you need to do is just go through the logs and check that for each user, let's say they log into your website every day or something like that. Okay, if they don't come to your website anymore, then you need to change something about your website to get them to come back. Okay, so the processing that you're doing on these user logs is very simple. Okay, you just check that every single day you have all your users coming back. However, you need to do this at massive scale. Okay, because you could have millions and millions of users, right? And then over many days, your logs can be terabytes in size. Okay, so you want to do some simple computation, but you want to do it on huge amounts of data. Okay, so so Google wanted to do this at some point, and it turned out that many other internet companies also wanted to do this type of data processing, and so this is how Mapreduce sort of grew in popularity. And eventually, Mapreduce is proprietary to Google. Okay, so they don't really share how they implement that system. But because other people wanted to have the functionality of Mapreduce, then later there was an open source version of Mapreduce called Hadoop, which was developed. Okay, so Hadoop basically does the same thing as Mapreduce, and it does it in basically the same way, but it's open source. Okay, and as I said, Mapreduce is actually very popular in industry. Okay, and just because many types of industrial applications fit well within this MapReduce model of simple computation on large amounts of data. And nowadays, there are also in academia, people are also sort of applying this data science paradigm. Okay, and so MapReduce is also used in academic settings for data processing. Okay, so before we talk about how the MapReduce system is actually designed, let's talk about some of the factors that influences the design. Okay, so so its design was based on certain assumptions about where you're going to run these MapReduce jobs and what types of jobs you have. Okay, so so the first assumption is that the hardware environment that you're going to be dealing with within this hardware environment, you're frequently going to have failures of components of your system. And this is because MapReduce was designed for these data centers, which have tens of thousands of servers, right? And then these servers can actually, so if you have tens of thousands of servers, then even if the individual servers are quite reliable, it's still quite likely that at any point in time, you have some servers which have failed. Okay, so so therefore, MapReduce was designed so that you can actually deal with having faulty components. Okay, another part of MapReduce's design is that since we're mostly focused on processing data, right? So the computation is rather simple, and it's mostly the data that we care about. And in fact, sometimes you could have very large amounts of data, but all you need to do with this data is to just sort of go through this data once. Okay, so you can stream the data once, and then that might be enough for you to do your computation. Okay. So in that case, what makes sense is to just, so originally the data is sitting on these different computers. Okay, so suppose that the data has been partitioned among the computers, so they're sitting, let's say, within the hard disks of the different computers. Okay. So now, since all we want to do is just to scan through this data once, okay, because many MapReduce jobs simply need to just scan through this data a single time or a few times. Okay. In that case, it doesn't make sense to move this data around. Okay, it's much better just to keep the data where it is. Okay, so if the data is sitting in the hard disk of some computer, then we're not going to ask that computer to transmit the data to somewhere else. Okay. Instead, if we need to do a computation on that data, we're just going to send the computation to that computer. So that computation is just a small piece of code, right? So we're just going to send that small piece of code to that computer, and then that computer can run the code on its data, and it never needs to move that data to another computer. So it doesn't need to incur the oh, I'm sorry about that. So that computer doesn't need to move its data, so it doesn't need to incur the cost of communication. Okay. All right. Another part of MapReduce's design is that we only oftentimes we only require sequential access to the data. Okay, we don't need random data accesses. So, for example, as you're scanning through the data, right, the computation, the computation that you're doing, the only data it needs is the data from, let's say, a single computer. Okay, so it needs to access like a chunk of data from that single computer. This is in contrast to if you need to have random data access, then perhaps in order to do your computation, you need data from multiple computers. Okay, in that case, you do need to have communication between these different computers. Okay. However, because MapReduce is oftentimes focused on these types of computations where you only need sequential data access, okay, then you don't need communication between these different computers. And this is good because MapReduce is usually running on these systems where the communication network is not very powerful. Okay, so if you needed lots of communication, then MapReduce would be very inefficient. Okay, but by focusing on the right types of jobs, then MapReduce can still be quite efficient. Okay, and lastly, MapReduce focuses on scalability. So basically, in MapReduce, you want to achieve something like linear scaling. Okay, so if you double your number of processors, you want to go twice as fast, okay, or process twice as much data in the same amount of time. And this is oftentimes possible because for MapReduce jobs, you usually don't have much overhead. So the main overhead would be communication. But as we said, in MapReduce jobs typically don't have lots of communication. And if you have a job which does have a lot of communication, then probably you should not run that in MapReduce. Okay, so the upshot is that there are certain algorithms which run very well in MapReduce, and we'll see some of them today. Okay. But there are definitely lots of other algorithms which do not run well in MapReduce. Okay, these algorithms would be any algorithm which requires doing many computation steps. Okay, that's not going to run well in MapReduce, because MapReduce is basically designed for these jobs where you can finish the entire computation in like a small, let's say, constant number of time steps. Okay, so yeah, and also jobs that have lots of communication are not going to run well in MapReduce. Okay, so that's the basic philosophy behind MapReduce's design. So now let's actually talk about what this MapReduce model is. Okay, so MapReduce is based on a data structure, a simple data structure, which is key-value pairs. So everything in MapReduce basically boils down to somehow processing these key-value pairs. Okay, so a key-value pair is simply, well, it's a pair, okay? And the first component of that pair is a key, and then the second component is a value associated with the key, okay? And so here, the keys can be, like, for example, numbers, like integers, or floats, or strings, or anything which, so the key is used to refer to the value, okay? So for example, the key can be like a person's name, okay? And then the value can be some information about that person. Okay, so we're using the person's name to refer to information about him. Okay, the key can also be like an integer. So for example, this can be the person's some sort of ID for the person. Okay, so you can refer to the person through his ID instead of his name also. And then the values can be arbitrary. Okay, so they're just some sort of information that we're trying to keep track of. So so they can be sort of like, tuples. So if we're talking about a person's information, right, we can have, his age, his address, his other types of information. Right, so those can all be values associated with that key. Right, yeah, and so we can have arbitrary data structures as the values. And all of the computation in MapReduce is based on these key value pairs, as we'll see. Okay, so somehow we, even if we start with some sort of data which is not necessarily expressed in terms of key value pairs, we're going to convert that data into these key value pairs so that we can process it if we want to use MapReduce. Okay. All right, so as an example of this, suppose we're trying to process a set of web pages. Okay, so we need to somehow represent these web pages as key value pairs. And one way to do that is the keys can be the URLs of the web pages. Right, so that's like an identifier for the web page. And then the value can simply be the content for the web page. Okay, another example is if we want to process a graph. Okay, so graphs are usually expressed in terms of adjacency lists or adjacency matrices or something like that. But if we want to process them in MapReduce, we have to somehow convert a graph into a key value type representation. And one way we can do that is that we can make the keys be the IDs of the nodes in the graph. Okay, and then the value associated with each key. Right, so then that would be the information associated with each node. Well, that information can just be like the adjacency list for that node. Okay. Okay, and then a MapReduce computation has two parts. Okay, so so just like this entire model is called MapReduce, right? There are just two parts to a MapReduce computation, which are the map step and the reduce step. And so what these two steps do is that, so first of all, the map step is going to take a key value pair. Okay, so here K is a key and V is a value. And then from that key value pair, it's going to produce a list of key value pairs. Okay, so it starts with one key value pair and then produces possibly a big list of key value pairs. Okay, it could also sometimes just produce a single other key value pair, but it could also produce multiple key value pairs. And then the the reduce step. Okay, so in a MapReduce computation, you first do the map step, right, and then you do the reduce step after that. And the reduce step, what it does is that it's going to take a key and then a list of values associated with that key. Okay, so maybe for the same key, we have multiple values associated with that key. Right, so for example, if key is a person's name, right, we could have multiple values. So for example, the the person's address, the person's telephone number, and stuff like that. Okay, so it's going to take this key and then a set of values or a list of values, and then it's going to produce another list of key value pairs. Okay, so you see that everything in MapReduce reduces down to somehow processing these key value pairs. Okay, and the MapReduce program is where you get to define how you transform a key value pair into, how you do this mapping transformation from one key value pair to like a bunch of key value pairs. Okay, and also the programmer is going to define how this reduce operation works, right? How you go from this to like a bunch of key value pairs. Okay, now some things about how MapReduce is actually implemented. So initially, the input to a MapReduce job is a set of key value pairs, right? Because the first step to a MapReduce computation is to start with some key value pairs. Okay, and so so these initial key value pairs are going to come from the inputs, and the inputs are initially usually stored as files in some sort of distributed file system. Okay. And then the first thing is that, these files, when you start to run the MapReduce job, then these files are pulled off of the file system, right? And then they're distributed to multiple servers. And then each of these servers is actually performing the map or reduce tasks. Okay, so then, we have we have servers. So we have servers both for the map tasks and for the reduce tasks. And for the map servers, right? So they're going to execute this map function. Okay, so the map function is the one that transforms this key value pair to this list of pairs. So they're going to execute that function, and then they're going to execute it on all pairs of key value pairs in the file that it gets. Right? Because initially, we take these files and we distribute it to the map servers, and each file can have many, many key value pairs. Okay, so the map server is just going to apply this map function on every single key value pair that it receives. And then this is going to lead to an output of a bunch of key value pairs. And then we're going to call this output of key value pairs. So this is not our final answer yet. Okay, so therefore we're going to call these intermediate key value pairs. Okay, now using these intermediate key value pairs, the next step that the MapReduce system is going to do is that it does a so-called shuffle and sort stage. Okay, so this is provided automatically by the MapReduce system. Right, the programmer doesn't have to write this stage. Okay, this is just built into the MapReduce system itself. And what this shuffle and sort does is that it's going to take all of the so previously for the mapping stage, we output a bunch of key value pairs. And now the shuffle and sort is going to take all of the values associated with the same key. Okay, so for one key, you could have multiple values which were output, right? And so it's going to take all of the values associated with the same key and group them together. Okay, so now you have a bunch of, so this is why you have, for example, in this reduce stage, you have a single key and a bunch of values, okay? Because we're going to take all of these intermediate values, which were generated, and then for all the values which have the same key, we're going to put them together in the shuffle and sort stage. Okay, and then we're going to provide those pairs, the grouped pairs. Well, first of all, we're going to take these grouped pairs and we're going to partition them. Okay, and then we're going to take each of these partitions and then send it to a reduce server. So if we have 100 reduce servers, we would generate 100 partitions. Okay, so therefore, for each reduce server, the reduce server is going to get a bunch of these key value pairs, and for each, if you look at all the pairs that the reduce server gets, well, these are going to be sorted by the key. Okay. On the other hand, if you look at two different reduce servers, then their pairs do not have to be sorted. Okay, and then the last step to the Mapreduce computation is that the reduce server is going to execute its reduce function on all the key value pairs it receives. Okay, and then it's going to produce a bunch of key value pairs. Right? And then these key value pairs are going to be written back to the file system. Okay, so remember that initially at the beginning of the computation, all of the data, right, they were sitting as files in some sort of file system. And then when you start the computation, you first pull these files off the file system and then give it to the map servers. Right? So the map servers are going to produce these intermediate key value pairs. Right? And then the Mapreduce runtime is going to shuffle and sort these. Right? So it's going to group together all the pairs with the same key. And then it's going to distribute these grouped data key value pairs to the reduce servers. The reduce servers do some more processing on these key value pairs, and then it writes it back to the file. Okay, so this is sort of like one cycle of the Mapreduce computation. And in a real Mapreduce job, you could actually do multiple ones of these cycles. Okay, so you get data from the file system, do some processing, and then write the data back. Okay, and then you do some more, and then you can do this again. Okay, then you pull your data off the file server again, do some more processing, and then write it back. And then you can keep doing this. Okay, so you can iterate multiple times. But usually, many Mapreduce jobs do not iterate that many times. Okay, so they might do this, a few times, or at most a few dozen times. Okay, but for most Mapreduce jobs, we're not supposed to do this process like thousands and thousands of times. Okay, whereas in a normal parallel computation, right? So basically, each one of these cycles corresponds to, if you think back to the PRAM model, okay? So each of these cycles corresponds to sort of one step in the PRAM model, okay? Or maybe two steps in the PRAM model. And remember that for the PRAM model, we often ran these algorithms for many steps, for example, for logarithmic number of steps, okay? Well, in Mapreduce, you're usually not going to do that. You might run this algorithm for a constant number of steps. Okay, and the reason is because each of these steps is actually quite expensive, right? Because to do a step, you need to pull data off of the file system, right? So that's a lot of work because you need to read from the file system, and then you need to communicate that data, right? And then you need to do some processing, and then you need to do this shuffle and sort stage. And this is also expensive because in this shuffle and sort stage, we actually need to sort everything by the key. And if we could have billions and billions of keys. So the runtime needs to actually sort like billions or billions of values. Okay, so this is this shuffle and sort is expensive, right? And then after the shuffle and sort, you need to partition the data and then send it to these different reduce servers, and that's also expensive. Okay, and then finally, after the reduce servers are finished, they need to write all their data back to the file system, and that again is very expensive. Okay, so each cycle for the Mapreduce is actually quite expensive. Okay, so this is why we want to only run jobs which can be completed in a few cycles. Okay, so all that is about the basic design of Mapreduce. So now let's finally look at how do we actually write a program in Mapreduce. Let's look at some example programs in Mapreduce. Okay, and by the way, all these examples are coming from this book called Data Intensive Text Processing with Mapreduce by Lin and Dyer. Okay. All right, so the first example we're going to look at is a simple Mapreduce job, which is going to count the number of occurrences of different words in several documents. Okay, so imagine that you have a bunch of web pages. Okay, so each web page has a bunch of words, and you just want to count how many times each word occurs in these web pages. Like how many times does this say cat? How many times does this say dog? Or something like that. All right, so then the way this is going to work is, so here is our program for doing this computation. Okay, what we're going to do is we're going to go through, so we have multiple ones of these documents. Okay, so we're going to go through each document. Okay, the document is going to be called D over here. And then we're just going to parse this document and extract all these individual words. Okay, so each T here is one word from the document. And then from this, and then based on this term, we're just going to output a key value pair. Okay, so the key is going to be the word, and the value is just 1. Okay, and this 1 simply indicates that, well, this word occurred once. Okay, and if the word occurs multiple times, then we represent that by emitting multiple ones of these key value pairs. Right, so if like cat occurs 3 times, then we would actually output cat 1. We would emit that 3 times. Okay, so then the mapper is going to do that on all of the documents that it receives from the file system. Okay, so it's going to output a bunch of these key value pairs. And then, let's look at the diagram over here. Okay, so imagine that these are files, and then these files are distributed to the mappers. Okay, and so then the mapper is going to go through all of these files, and it's going to say that, okay, A occurred once. Okay, so there's one tuple A, comma 1. Okay? And then maybe B occurred twice, so there would be 2 tuples B, comma 1. Okay, and then for a different mapper, right, maybe he saw that C occurred, so he would have 9 occurrences of C. Okay, so he would have like, C, comma 1, that would occur 9 times. Okay, so anyway, so all of these mappers are after they run their mapping function, they're going to produce these tuples, okay, these key value pairs. And then we're going to do the shuffle and sort stage. Okay. So the shuffle and sort stage is going to take all of the values associated with the same key and then group them together. So for example, here, A is associated with this value 1, and then over here on the third mapper, there were 5 A's. Okay, so therefore, the shuffle and sort stage is going to group this 1 and 5 together, and it's gonna that's going to be associated with key A over here. Okay, so likewise, B, right, that was associated with, this value 2. So there were 2 B's over here, and then 7 B's over here. And the shuffle and sort is going to group all of these together, right, with, with this B. Okay, and likewise for the C, it's going to group together all of the occurrences of this C. Okay, so there were 9 occurrences here, there were 2 over here, and there were 8 over here. So it puts all that together. Okay. And then now the reducer, okay, so now we get to the reducing stage. Okay, so the reducer is going to get, for each word, okay, so for example, for A here, okay, it's going to get a bunch of these counts. So A, occurred 6 times. Okay, so it would actually get, A, comma 1, it would get 6 occurrences of these. Okay, and then so it's just going to, and then the reducer is just going to, for each term, it's just going to go through all of the counts associated with that term and just add them up. Okay, so in the end, it would get that the sum for A is equal to 6. And then it would just emit, A, comma 6 over here. Okay, but by the way, this picture is not exactly corresponding to this computation over here. Okay, but I'm just using this picture just to show what the main steps are, right? So the main step is to read the data to the mappers, right, to output these pairs, to shuffle them and sort them, and then the reducer does some stuff. Okay, but in the end, you see that here for each word we have all the all these counts which were ever detected for that word. Okay, so anytime you saw the word cat, right, you output a cat 1. Okay, so then this over here, the reducer would get counts for all the occurrences of cat. Okay, would add them up, and then that's the total number of times that cat occurred. Right. Yeah. Okay. Okay. Now, a few more details about this. So the Yeah, so when you start a MapReduce job, you could actually create many map and reduce tasks. Okay, so you can create like thousands or even more of these MapReduce tasks. But when it comes time to run them, you might not have that many servers. Okay, so therefore you need to take your thousands of tasks and maybe schedule them onto like a few dozen servers. And the way this is done is that each server has like a queue. Okay, has a work queue, and then you can enqueue multiple tasks into the queue at the server. Okay, another important detail is that the map stage comes before the reduce stage, right? And in fact, the reduce tasks, okay, so we could have many reduce tasks and many map tasks, but these reduce tasks can only start after all of the map tasks have finished. So that means that even if you have one map task, which is somehow taking a long time, okay, this is going to prevent all of the reduced tasks from starting, right? So if you could have like 100 computers dedicated to reduced tasks, okay, but all of these computers are going to sit idle until all of the map tasks have finished. And so this means that your performance is very sensitive to stragglers, which are tasks that take much longer than other tasks. So if you have one map task, which is, for example, very poorly load balanced, okay, so it's got much more work to do than the other map tasks, then that's going to prevent any of the reducing tasks from starting. And that's going to give you very bad performance. Okay, or you could have maybe faulty hardware. So you assign some jobs to a computer and that computer crashed. Okay, in that case, you assign some map tasks to the crashed computer. In that case, you're never going to finish your map tasks, and then your reduced tasks are never going to start. Okay, so to deal with this, you need some sort of failure detection mechanism, right? So you need some maybe like heartbeat mechanism where you require each computer to periodically send you a message to tell you that they're still working. Okay, so the reduce stuff can only start after the map tasks are finished, but the shuffling step, okay, so this can actually happen while the map tasks are still executing. Okay, so there can be some overlap between these two steps. Okay, the other thing is that we said that usually MapReduce is going to move code to data. Okay, so it tries not to send data around because the data can be quite large. However, if you get a computer which is which already has too much work to do, okay, it's been assigned many tasks, then then it can't process all that data. Then it can't process all the data it's been assigned. So in that case, MapReduce could move some of the data from that overloaded computer to a less loaded computer. Okay, so something else about MapReduce is that there are some things which are, some parts of it which are designed to optimize its performance. So for example, there are these programs called partitioners and combiners, okay? And so these are like functions that the programmer can create in order to improve performance. And basically, so if you look at a diagram, then what's going to happen is, so these combiners and partitioners are optional. Okay, they're only there if you want to improve performance. But if you write the combiners and the partitioners, then first of all, the map tasks are going to run. And then the outputs are going to get fed through this combiner function. Right? And then they're also going to get fed through this partitioner function. And then they're going to get shuffled and sorted. Right? And then they go through the reducer. Okay. So now what this partitioner does is, so the partitioner is a function, so it's going to specify which reducer each of these intermediate key value pairs gets sent to. Okay, so remember that the mapper is going to produce a bunch of these intermediate key value pairs, okay, and that's going to go through the combiner, and so that combiner basically reduces the number of these key value pairs, okay, but the combiner also outputs a smaller number of intermediate key value pairs. And then these go through the partitioner, and the partitioner can decide where, which reducer processes each key value pair. Okay, so for example, the partitioner can try to load balance between the different reducers. And one way it can do that is that it can take a key and then map it to a random reducer. Okay, so basically, it can take this key and then let's say it'll apply a hash function right? And then it'll take this modulo r, where r is the number of reducers. Okay, so then this gets you a number between 0 to r minus 1, corresponding to a reducer. And then the partitioner will just take this key value pair and then send it to that reducer. And so the hope is that by doing this, we can actually load balance between the number of key value pairs that each reducer receives. Okay, so this usually this works pretty well if for each key it has about the same number of values. Okay. However, if you're in a situation where maybe there's one key that's like very popular, okay, so that one key has like a million values associated with it, okay, and all of the other keys have just like a small number of values. Okay. So in that case, you're still going to have to map that key to some reducer. Okay, so whichever reducer gets that super popular key, that reducer is still going to be overloaded. Okay, so basically, this hashing technique doesn't always work. Okay, but it works well when the keys are pretty balanced. Okay, so that's for the partitioners, and now for the combiners. So the combiners are basically they do some sort of a local key aggregation after the mapping stage, and then before the shuffle stage. Okay, so you can kind of think of them as like mini reducers. Okay, so for example, here if you have a mapper that output. So this is going back to our text counting example, right? The previous example. Okay, so if the mapper said that okay, he saw like 3 copies of C, and then later on he saw 9 copies of C. Okay, then you can actually just combine those and say that you saw he saw 3 copies and then 6 copies. Okay, so he saw a total of 9 copies. Then the combiner function can actually just combine those 2 key value pairs into a single key value pair. Okay, it just says that it saw 9 copies of C. And so later on, that would mean that when you do the shuffle and sort stage, right, you have less data to sort. Okay, you have 1 key value pair here instead of 2 key value pairs, and also you have less data to transmit to the reducers. Okay, because you just transmit the single key value pair as opposed to 2 of them. Okay, so this is how the combiners improve performance by sort of preemptively combining as many keys as possible, so that you have less stuff to sort and then less stuff to communicate to the reducers. Yeah, right. So in the word count example, right, it can take, if the mapper itself saw many occurrences of a word, then it can just combine all of those into a single count. Okay, now there's no guarantee that at runtime, the Mapreduce system will actually run your combiners and partitioners. Okay, so so you can write them, but I guess the system is not guaranteed to actually run your programs for you. Okay, so now let's look at some other tasks that we can do with Mapreduce. Okay, so so the first problem that we try to solve is filtering. Okay, so here we initially have a big set of data, right? And then we want to keep a subset of that data which satisfies some condition. Okay, so let's say you have a bunch of numbers, and you just want to keep all the numbers which are above a certain value. Okay. Yeah, and so this can be this has a bunch of applications. So for example, you can use this to filter out and just keep the interesting data. Okay, you can also use this to clean your data. Okay, so you can have some criteria for whether this data is valid or not. Okay, so you can filter out all the invalid data. Okay, or you can sample the data. Okay, so so your condition can be like if some random number it meets a certain value, then you're going to keep that data. Okay, so this would be a way of sampling through all of your data. Okay, so it's actually very easy to do filtering in Mapreduce. In fact, we don't even need the reducers. Okay, all we need are the mappers, because each mapper is simply going to go through. So we assume that the data is stored in this key value format. Okay, and we're trying to keep keep the pairs where the value or the key satisfies some constraint. Okay, oh, I guess the value. Okay, so the condition is going to be on the values in the key value pairs. right? And so the mappers, each mapper is going to get a subset of these key value pairs, and it's just going to look through each key value pair and then keep the ones that satisfy that condition. Okay, so yeah, so that's all we need to do, and we don't even need any reducers. Okay, so after the mapper is finished, it's going to output all the key value pairs which satisfy that condition. Okay, so we've so that accomplishes the filtering task. Okay, so the next task is so suppose that we want to keep let's say the the top 10. We want to make a top 10 list of from our data. Okay, so we have so the data is storing some information, and then we have a way of ranking that information. Okay, we want to keep like the best information, like the best 10 pieces of information. So then so we're going to assume that we have some sort of ranking function for each input pair, and the ranking function says like how good that pair is. Okay, and we only want to keep the top 10 best pairs. Okay, so this can be used to find things like outliers. Okay, so we want to take the top 10 most irregular pieces of data, and then maybe you want to throw those away. Okay, or you can take the top 10 pieces of data and keep them. Okay, so you can take like the most interesting top 10 pieces of data and keep them. Okay, so to do this, we're going to use multiple mapping tasks, but only one reduce task. Okay, and so the mapping tasks, each one of them is going to get a subset of the data. Okay, a subset of the key value pairs, and it's just going to go through that subset and then take the top 10 ranked key value pairs from its subset. Okay, so if it gets like 1,000 pairs, right, it's going to take the top 10 of those, and then for each of the top 10 values that it decides to keep, it's going to output let's say a null value pair. Okay, so there's not going to be, it's just a null key, and then the value that it wants to keep. Okay, so then all of the values are associated with this null key. Okay, so then when you sort them, and they're all going to get sent to the same reducer. Okay, so this null is going to be associated with the top 10 values from each mapper. So if you have 20 mappers, they each produce 10 values, so then you get 200 values. Okay, and they all get sent to the reducer, and the reducer is going to look through these 200 values and then just take the top 10. Okay, so then that would be the top 10 overall values. And this is scalable because usually you're not going to, each mapper is only going to output, let's say, 10 values here. Okay, so even if you have lots of mappers, like thousands of mappers, right, this reducer is only going to get 10,000 values, and so it could easily just go through all these values and take the top 10. Okay, so the next task is, so let's say that we want to find distinct values in the input. Okay, so for example, we want to do deduplication. Okay, so we have a bunch of key value pairs, but some of these values might be repeated. And so we want to take all of those out. And so the way we do that is that, so each mapper is going to take, for each key value pair that it receives, it's just going to output the value. Okay, so the value now, so the value now becomes the key. Okay, it's going to produce a key value pair where the value is now the key, right? And there's actually no value associated with this key. Okay, so it outputs one of these things for each of its key value pairs. Okay, and now in the shuffle stage, right, all of these things, okay, all of these things with the same value are going to get grouped together. Okay, and then they're going to get sent to the same reducer, right? Because all of the during the shuffle stage, everything is grouped by the key. Okay, but here the value is the key, so therefore all of the all the things with the same value get grouped together, and then they get sent to the same reducer. Okay, and now this reducer is just going to iterate through its the pairs that it receives. Okay, so maybe it receives if this value here is let's say 5. Okay, maybe it received 3 copies of 5. Okay, but then as it iterates through them, right, it's just going to output a single copy of 5. okay, even though it received 3 copies. And so that is a way to for us to produce only the distinct keys, right? So we only output 1 copy of each value. Okay, so here we can actually use the combiner to do some sort of pre-combining, okay? Because for example, if we have multiple copies of a value, right? Then the combiner at the combiner stage, we so the combiner is running on a single mapper, right? And that combiner can actually take all the copies of the value that this mapper saw, and it can just keep just a single copy of those. Right? So if it saw like 3 copies of 5, okay, it'll just keep a single 5, and then it'll output that single 5 into the shuffle stage, and then only a single 5 will get sent to the reducers, okay, from this mapper. Right? From other mappers, you might get additional copies of 5. Okay, so you still need the reducer. Okay, but at least we're not going to send like multiple copies of 5. Okay, yeah, and this is quite a scalable approach. In fact, you can just increase your number of mappers and reducers until eventually the communication starts to dominate. So the communication is just that we're going to be producing many of these value null pairs. Okay, so if you produce too many of them, then you're going to have a large shuffling cost and communication cost. And so this is why the combiner is useful. Okay, because the combiner can reduce the number of these pairs. Okay, so the next task is let's say that we want to okay, so let's say that we want to implement a join function. Okay, so a join function is something which is used, for example, in databases, and it's used to combine data from two different tables. Okay. And there are multiple types of joins. So there's like inner joins, and then left joins, right joins, and so on. And so today we're just going to consider inner joins. Okay. So the way inner joins work is that we're going to so the input to this operation is going to be 2 tables. Okay. And furthermore, we're going to have a predicate. And what we're going to do is we're first of all going to form the Cartesian product of these 2 tables. Okay, so I'll show you what that means later. Okay. And then for this Cartesian product, so this is going to produce a bunch of rows which are formed from these 2 tables. And then we're going to run the predicate over all of these rows, and then only keep the rows which satisfy that predicate. Okay, so let's do an example of this. So for example, suppose we have 2 tables here, like we have, let's say this table A, right, and then this table B. Okay, so we want to join A and B, and then the predicate we're going to use is that we only want to keep the rows where the user ID from A equals the user ID from B. Okay, yeah, so in fact, we're going to call this user ID the foreign key. Okay. But anyways, so what it means to join A and B using this predicate is that what we'll do is we'll go through each, we're going to first of all form the Cartesian product of A and B. Okay, and to do that, we're going to go through each row of A, and we're going to sort of combine it with all possible rows of B. Okay, so for example, this first row of A, right, with this user 3 over here. Okay, we're going to try to combine that with this first row of B, right, the second row of B, and then third row, and all of the rows. Okay. However, notice that with this predicate over here, we only want to keep the rows where where A's user ID equals B's user ID. Okay, so A's user ID is going to be 3 over here, right? So when you when you combine A with this first row, right, we're going to keep that because here the user IDs match, right? When you combine A with the second row, right, the user IDs also match, so we're going to keep it. But then when you combine A with like the third row and all of the other rows, then the IDs don't match, and so we're not going to keep those. Okay, so therefore we're going to keep this one and then these 2 things. Okay, and in fact, you see that this is going to be part of our output. Okay, so this is the output from the join operation using this predicate. Okay, all right, so then we're going to keep going with the rest of A. So then we're going to take the second row of A, and we're going to try to combine this with all of the other rows of B, right? And we only want to keep the ones where the user ID from A and B are the same. But you see that in B, there are no users with ID 4. So therefore, we're not going to combine this row of A with anything from B. Okay, and then next, we're going to go through the next row of A, which has user ID 5. Right, we're going to try to match it to all of these other rows of B, and it's going to match with these two rows. And so these two rows are going to be part of our output also. Okay, and then finally, we go through this row of A, and we see that this user ID from A doesn't match anything from B. And so therefore, we're not going to produce any output from this row of A. Okay, so in the end, this is the output that we want to produce from the inner join. Okay, so in order to do this computation, yeah, so what we're going to do is the mappers are going to right. So the mapper is going to go through each of the table. Okay. So each mapper gets part of the first table and part of the second table. So he's going to go through every record, every row in these two tables. Okay. And then he's going to extract the foreign key, the user ID. Okay. And also the rest of the key. Okay. So yeah. So this is the user ID is a foreign key, and this is the rest of the information for that key. Okay. And likewise, he's gonna in B, he's also gonna extract the foreign key and then the other information. Okay. Yeah, and then that mapper is gonna output a pair. Okay, so the pair is gonna be the user ID, and then the rest of the information in that row, right? And then one more value x here. Okay, so x is just indicating whether it came from the first table A or the second table B. Okay, so x can be like just a single bit here. Okay, indicating which table it came from. Okay, now the shuffle the shuffle stage is going to take all of the these pairs with the same user ID, right? And it's going to send them to the same reducer. Okay, so that reducer is going to get let's say some sort of user ID over here, and then a bunch of records associated with that user ID. And then this information can come from either the first table or the second table, right? And the way you can tell is that you can just look at this bit over here. Okay, so the reducer is going to get a key and then a bunch of these records plus these bits, right? And then each time that he sees like a record from from two different from two different tables. Okay, then he's gonna make he's gonna okay, so he's gonna do this. Okay, he's gonna go through all of these key value pairs. He's gonna take all the ones from the first table. Okay, where x is, let's say, 0. Okay, he's gonna put them into a list L1, and then he's gonna take all these pairs where they come from the second table and then put them into a list L2. Okay, and then he's gonna do a nested loop over L1 and L2. Okay, so for each record of L1, he's going to combine this with all of the records of L2. Okay, so in total, this is going to form like L1 times L2 number of records. So the next problem we're going to look at is a word co-occurrence. Okay, so the setup for this problem is that suppose we have a set of words, and then we want to count the number of times that a pair of words occur together in some context. Okay, so for example, in a sentence or in a paragraph or in an entire document. So the basic idea is that if these pairs of words occur together in a sentence, for example, then they might be related to each other. Okay, whereas if they don't occur in a sentence, then they're less related to each other. So we basically want to find out how related are certain pairs of words. And this has a bunch of applications in things like text mining or like mutual information and things like that. Okay, so the way we're going to do this is that well, we need to define what a context is. Okay, so we're trying to find either co-occurrence in a sentence or paragraph or some other sort of unit of co-occurrence. Okay, we have to specify how large the area is that we consider things to be co-occurring in. So yeah, so then we're going to use a function called neighbors to define this. Okay, so so neighbors of W is going to be all of the words that co-occur with the word W in some context. So for example, if we're using sentences as our context, right, the neighbors of W would take a word from a sentence, and then it would produce all of the other words in that sentence. Okay, so we're going to assume we have this sort of function that gives us the context and all of the words that co-occur. And now we're going to look at two different ways of implementing this, of counting word co-occurrence. Okay, so the first method is going to be called the pairs method. So basically here, what we're going to do is for each document that we're processing, right, and then for every word in that document, okay, we're going to use this neighbors function, and we're going to find all of the other words U which co-occur with this word W over here. And then just for each pair of these, each pair of W and a co-occurring word, we're going to output a count of 1. Okay, and then the reduce function is just going to take a pair of words, okay, and then it's going to get a bunch of counts for these words, right? So each of these counts is basically going to be 1 or some other number that says how many times it's been observed that W and U co-occur, okay, and then it's just going to add up all of these counts, and then in the end it's going to produce that word pair plus the total number of times that they co-occurred. Okay, so there's another approach for doing this, which is called the stripes approach. So the stripes approach is going to take each word. So the pairs approach is going to say, for each word and each co-occurring, each neighboring word in the same context, it's going to output a pair. Okay, so you could have many different pairs for each word W over here. Now the stripes approach is going to only emit one pair per W. Okay, and so in order to keep track of the words that co-occur with W, it's going to use this associative array. So for example, something like a Java map. Okay, so then in the mapper function, right, we're going to again go through all of the words which occur in this document. Okay, and then for each word, we're going to create a separate associative array for that word. And now for all of the neighbors of that word, okay, we're just going to store these neighbors in this array. And then in the end, we're just going to output the word plus its array. Okay, so this array is going to contain all of the words that co-occurred with W. And then for the reducer part, right, so then what's going to happen is that, so for each mapper and for each word, that mapper is going to produce one pair of this form for that word. Okay, and so the reducer, what it's going to get is for each word, it's going to get a bunch of these associative arrays, right? One from each mapper. And then we're going to assume that we have this function. So let's see. So let's assume that we have some way of merging these arrays. Okay, so for example, if we're using this Java map, right, then that library has this merge function that can take several arrays and combine them. Okay, and then after we combine them, we can get a count of how many times, how many total occurrences are there with this word and different other words in the pair. Okay, yeah, so those are the two approaches. And we can actually do a comparison between these two approaches. So before we do that, we can first say that we can use combiners to improve the performance of both approaches. Okay, so the combiners would basically, especially for the pairs approach, if we just do the basic pairs approach, then for each word we can actually output. We have many pairs starting with that word, right, and then some other word in the context. Okay, so for each W we have many different U's. Right, so we would be outputting many of these key value pairs to the reducers. Okay, and so that's inefficient. So then what we can do is, I'm sorry. So I said that kind of wrong. Okay, so what we're trying to do in the mapper is that for each pair, okay, we're trying to combine as many of these pairs as possible. Okay, so for each of these W pairs, right? We're trying to combine as many of them as possible. Right, and that's just to reduce the amount of work that the reducer and the shuffle stage have to do. Okay, so we can use a combiner to sort of pre-combine these word pairs, these WU word pairs. Okay. Yeah, so in the pairs approach, yeah, maybe this actually does not work that well because you know, it might not be very likely to get multiple occurrences of the same word pair. Okay. I mean, you're going to have many occurrences. If you just fix W, right, you're going to have many different occurrences or many other U's co-occurring with W. But if you fix both W and U, right, then because the mapper is only processing you know, a small subset of the entire data set, then he might not actually observe too many co-occurrences of W and U. And if you don't have too many co-occurrences of W and U at that mapper, then the combiner for that mapper might not be very effective. Okay. All right, so that's one thing that we can do. Now, something else is that you know, these stripes are the stripes approach is going to hold the associative arrays in memory, right? Because that's how we can keep adding things to it. Okay. Or yeah, and if we have very large files, then it's hard to hold the entire associative array in memory, right? Especially because the in the stripes approach, we're not just processing one word at a time, right? We have one of these arrays for every single word in the document. Okay, and so we basically have to keep the entire document in memory, right? So initially, the document is sitting on disk in the at this mapper processor, right? And then we're reading parts of this stuff from the disk into the memory. But if we're using this associative array approach, right, then we have to keep all of this in memory. Okay, and this might not actually work if there's if the file is too large. Now, for the pairs approach, you actually do not need to keep things in memory, okay? Because every time you generate one of these pairs, right, you can just write it out to disk. Okay, so the yeah, so the pairs approach can be you know, it's not going to be limited by the memory. Okay, so then they actually did some comparisons between the between these two approaches. So they took 2.3 million documents, okay, which have a total of 5.7 gigabytes in size. Okay, and then there they used a co-occurrence. Just it's a sliding window of size 2. Okay, so it's just counting whether you know, words were consecutive with each other. Okay, just yeah. And then they used 19 nodes with 2 single core processors each. And then they compared the pairs and the stripes approach, and they found that the pairs approach produced 2.6 billion intermediate pairs. Okay, and then if you do the combining, you can reduce that by about a factor of 2. And then this came out to so the total files, the size of all those pairs was like 31 gigabytes. Okay, and it output a total of 140 million key value pairs. The reducers. Okay. And on the other hand, if you use the stripes approach, right, then this produced far less intermediate pairs, okay? Because in the stripes approach, each intermediate pair is going to be a word and then an array listing all of the co-occurrences with that word, okay? So it's going to be a lot less than the pairs approach. And then, in fact, the combiner was very successful. So here, if you do the combining, you go from 650 million down to like 30 million, okay? Now, the total size is a bit larger, right? Because in the end, you know, the pairs approach and the stripes approach, they have to produce the same answer, okay? So the stripes approach contains all the data that the pairs approach contains. And furthermore, because it's using a data structure, the associative array, to keep track of things, it actually used a bit more memory, okay? Or storage, rather, okay? And then in the end, the number of key value pairs it produced was also far less than the pairs approach. Okay, it was only 1.7 million, because again, each key is tied with an entire array as opposed to individual words. And then, so now which one performs better? Well, because the stripes approach is going to have, especially after combining, it's going to have far fewer, it's going to produce far fewer key value pairs, right, than the pairs approach. Okay, then we see that the running time for the, so here we have the stripes running time. Okay, and then here we have the pairs running time, and you see that the stripes method is going to be a lot faster. Okay, it's something like, what is this, about 7 times faster. Okay. And also, but both of these approaches are very scalable. Okay, because because we take the entire document and we just chop it up into parts, and so there's not much communication between these different nodes, since we only have 19 nodes here. Okay, so so they measure the scalability, and right, and then as you add more nodes, we're getting basically linear scaling over here. Okay, for the stripes approach. Yeah, the pairs approach might not scale so well because it has more communication, right? Because we produce more intermediate pairs, so there's more work for the shuffle stage. Okay, so up to now, we've been talking about problems involving numbers or strings, right? So now we're going to talk about some graph problems and how we can solve these in Mapreduce. Okay, so the first problem we're going to look at is breadth-first search. Okay, so so breadth-first search, we're given some sort of root node, and then you just want to find the shortest number of hops of every other node from this root node. Okay, so BFS is different from the previous tasks in that BFS is an iterative algorithm. Okay, so you can't just solve BFS in one pass. Okay, in one parallel step. We need to take multiple parallel steps to solve BFS. Whereas for all of the previous problems, we basically took one step or maybe a few steps and we solved them. Okay, BFS, you're going to have to take a variable number of steps. In fact, for the algorithm we're going to talk about, the number of steps you're going to take is going to be the diameter of the graph, or not the diameter, but the let's call it the radius of the graph. Okay, so it's the number of hops from your source node to the farthest node. Okay, we're going to call that the radius, and we're going to have to run Mapreduce that number of times. So remember that each time you call Mapreduce, you do the map, the shuffle, and then the reduce functions. Okay, so that's like one cycle of Mapreduce. And for BFS, we're going to have to go multiple cycles equal to the number, the radius of the graph. Okay, so so what we're going to do, so in each cycle that we're going to run Mapreduce for, we're going to compute one additional distance. Okay, the nodes at one more hop away. Right, so the first iteration of Mapreduce, we compute all the direct neighbors of the source node. Okay, and then the second iteration of Mapreduce, you compute the 2-hop neighbors. Okay, next iteration, 3-hop neighbors, and so on. Okay, so the so the way the algorithm works is that suppose we're in the dth iteration. Okay, so therefore we've computed all of the nodes up to d hops away from the source node. Right, and now we want now in the d plus first iteration of Mapreduce, we want to find all the nodes which are d plus 1 hops away from the source node. Okay, and so what we're going to do is right, so we're just going to go through all of our nodes, all these nodes over here, and then for each node, you're going to look at this node's current distance. Okay, so if the node is within, well, let's call it k hops. Okay, so let's say that we're in the kth iteration. So we've already successfully found all of the nodes within k hops. Okay, so so this distance is going to be, if you're within k hops, you're going to have we would have found the distance to this node, and otherwise the distance is going to be, let's say, infinite. Okay, and then for each of these nodes, we're just going to consider all of the neighbors of that node, and then we're going to set their distance to d plus 1. Okay. Now, this is not quite correct because, if you have a source node over here, right, and let's say that you have a node over here, right, then let's say that there's a path of length d like this. Okay. So then what this line does is that for each neighbor m of this node n over here, okay, so let's say there's a neighbor m1 over here and there's a neighbor m2 over here. Okay, so it's going to set the distance of, let's say, m2 from the source node to d plus 1. Okay, so d here is the distance to this node n. Okay, now this is correct, right? Because here what I'm drawing is that this node m2 over here is indeed one more hop away from S than N. Okay, so it is actually D plus 1 hops away from S. Okay. On the other hand, since we're considering all of the neighbors of N, there could also be another neighbor of N which is actually closer to S than N. Okay. And now this line would actually set that guy's distance also to D plus 1, right? Which is incorrect because his distance is actually D minus 1. Okay. Now we're going to find that this is okay because later on in the reduce part, right, we're going to basically look at all distances that other nodes claim for this node M1 here. Okay, so some nodes are going to claim that this node is, D plus 1 hops away, right? N is going to say that, oh, M1 is D plus 1 hops away. Okay, but then other nodes are going to say that M1 is only D hops away. And so we're going to take the minimum claimed distance for M1, and we're going to use that as the actual distance for M1. Okay, so basically we're going to fix up this D, and we're going to end up still using, we're going to fix up the D plus 1 and still end up using D as the distance for M1. Okay, so anyways, so we emit all of these tuples over here in the map stage, and then in the reduce stage, basically what's going to happen is that for each node, so what is the node called? So so for each node, we're going to have a bunch of these estimated distances for the node. Okay, and then we just want to take the minimum estimated distance for that node as the true distance for that node. Okay, so the node, I guess, is going to be called M, little m. Okay, so the node is called capital M, and the ID of the node is little m. Okay, but the distance that we're going to end up using for this M node is going to be the minimum claimed distance for M. Okay, so here we have a bunch of claimed distances for M. Okay, we're going to go through all of these, and then here we're going to take the minimum such claimed distance and use that as the distance for M. Okay, and so this is the correct thing to do. Okay, so this will fix this problem that we have up here where somebody was claiming that M1 is distance D plus 1, even though it's actually distance D. Okay, somebody else will definitely claim that M1 is only distance D away. So we're just going to end up ignoring the D plus 1 claim. Okay, now this algorithm for BFS is not work efficient, okay, because in each iteration, we're going to go through all of the nodes of the graph, okay. So this is basically, so this is like the Bellman-Ford algorithm, okay. Well, yeah, I mean, even though it's BFS, but anyways, it's not a work efficient algorithm. However, if we're in a setting where the diameter of or the radius of the graph is not too large, okay, then this is going to work okay. So for example, if if the radius of your graph is something like 6, okay, so maybe you guys have heard about this, 6 degrees of some actor, okay, some Kevin Bacon, he's some actor, but anyways, so what they're saying is that in many graphs that we encounter in practice, the diameter of those graphs is very small. It might be a constant number, a small constant number, like something like 6 or 10 or something. So in that case, this BFS algorithm is going to run for, let's say, 10 iterations. Okay, in each iteration, it's going to go through all of the nodes and all of the edges, right? So the total amount of work it's going to do is something like 10 times m. Okay, compared to a sequential BFS, which is only going to do order m amount of work. Okay, m plus n amount of work. Okay, so it's going to do 10 times as much work as the sequential algorithm, but because we're parallelizing across so many machines, then the performance of this is still going to be okay, right? However, if we deal with other types of graphs, so we talked about these graphs that have very large diameters, right? So for example, the map graphs, okay? So those, the diameter could be like several hundred or several thousand. So in that case, this algorithm is going to be very wasteful. And it could actually perform slower than the sequential algorithm. Okay, and then also, when is this algorithm going to terminate? Okay, well, this algorithm terminates when the nodes do not change their distances anymore. Okay, or when we've discovered all of the nodes. Okay, so those are two different termination conditions. And so what we're going to do is we're going to add like a new like driver program, okay, which is going to check whether we still need to keep running more iterations of this Mapreduce program. Okay, so if we've discovered all of the nodes, right, then at that iteration we can stop. Okay, so the driver program is responsible for detecting that condition. Yeah, okay. All right, and now we're going to look at a similar problem to BFS, which is a single source shortest paths. Okay, so the only difference with BFS is that in BFS, each edge has a weight of 1. Okay, whereas in this shortest path problem, each edge has some sort of positive weight, which is just sort of any number, okay, any positive number. And so in this case, we're just going to take the BFS code, and the only change we need to make is that instead of setting, when we're processing a node, okay, instead of setting all of its neighbors' distances to be d plus 1, we're going to set it to d plus w. Okay, where w here, so if we're processing a node v over here, right, then if u here is a neighbor of v, right, then we're going to set u's distance to be equal to d plus w, where w is equal to the distance, or sorry, the weight of the edge from v to u. Okay, so basically w is this weight over here. Okay, and then d is the distance to v. Okay. Yeah, and then and the termination condition is to check when all of the node distances have stopped changing. Okay, so again, we need like a driver program to check for this condition. All right, and then for every iteration, we're going to go through all of the nodes in the graph. Okay, and for each one of them, we're going to do this step. Okay, this relaxation step. So this is basically the Bellman-Ford algorithm for single source shortest paths. Okay, and this algorithm is also inefficient because because we need to go through all of the nodes in every iteration. Okay, there's a more efficient algorithm, Dijkstra's algorithm, but that algorithm is harder to parallelize. Okay, so so in terms of quantifying the inefficiency, well, this Bellman-Ford type algorithm is going to take order v times e amount of work. Okay, where v is the number of vertices and e is the number of edges. And then Dijkstra's algorithm, on the other hand, is going to take something like e plus v log v amount of work. Okay, so if v is not too large, then basically so this is doing sort of like v times more work than Dijkstra's algorithm. Okay, so this shows you, this is the single source shortest path is an example of a problem that you probably do not want to do on Mapreduce. Okay, unless your graph has very short diameter, then otherwise this inefficiency, right, this order v times e amount of work that you need for Mapreduce is going to overwhelm is going to be excessive. Okay, because if you do this sequentially, you're just doing this amount of work. So unless your diameter is quite small, okay, otherwise it's not worth it to do this problem on Mapreduce. So the final problem we're going to look at is PageRank. So PageRank is basically a way to rank the quality of websites, okay, and it's based on this simple idea where suppose I have a website and many other websites point to my website, okay. Well, that's an indication that I have a good website, right? That I have a high quality website, right? Because otherwise, why would so many other web pages point to my website? Okay. And furthermore, if the web pages point to my website themselves are high quality, okay, then that makes my website even higher quality, right? Because the fact that many high quality websites are pointing to my website indicates that my website is very, very good. Okay, so that's the basic idea of how PageRank is going to rank different websites. And and PageRank was made famous by Google, and Google actually used a version of PageRank in their early search engine. Okay, of course, in addition to PageRank, they also use many other heuristics to rank the quality of websites. Okay, but PageRank was one of them. Okay, so we're going to look at how to. So PageRank basically assigns a number to each website. Okay, and the higher the number, the better your website. And so the way that we're going to compute the PageRank number of a website is that, well, suppose we have a website n, okay? Then what we're going to do is we're going to look at all of the neighbors of n, Okay, so these are websites that are pointing to, so we're going to take all the websites and represent them by a graph. Okay, so for example, if we look at this figure on the right, then each one of these nodes is a website. Okay, and the websites point to each other, and so therefore we can represent this whole thing by a graph. And so in this graph, we're going to pick a node n, and then in order to compute n's PageRank, we're going to look at all of the neighbors of n. Okay, so L of n is denoting the all of the neighbors of n. And then for each each of the neighbors, so let's just, so for each of the neighbors, we're going to look at the PageRank of that neighbor. Okay, so P of m is the PageRank of the neighbor m, and then we're going to divide this by the degree of that neighbor. Okay, and then we're going to multiply this by this factor 1 minus alpha. So alpha here is like a number between 0 and 1. Okay, and then we're going to add this to this other part, alpha times 1 divided by g. Okay, so so what's happening with this equation over here is that so the PageRank kind of corresponds to the probability that a random that a person that's visiting the web in a random fashion, okay, that this user will actually end up at your website. Okay, so if there's a very high probability that somebody ends up at your website, then this is an indicator that you have a very high quality website. Okay, so then what is the probability that somebody ends up at your website? Well, so this, we're going to break this into two parts. Okay, so for the first part, we're going to assume that alpha fraction of the time, a user is just going to visit a completely random website. Okay, so therefore the probability that this, when he's visiting a completely random website, the probability he ends up at your web page is going to be, so alpha is like how likely he is to be visiting randomly, right? And then G here is the total number of nodes in this entire web graph. Okay, so so alpha divided by G is the probability that if you go to a random node, right, then this is going to be your node. Right? Condition, times the probability that you are actually visiting a random node. Okay. And the second part of this equation is that 1 minus alpha fraction of the time, the visitor, the user is not just visiting a random node. Okay. Instead, he's going to arrive at your website n through one of the neighboring websites. Okay. So so what is the probability that he's visiting one of the neighboring websites? Right. Well, for each of these neighbors m, he's got a p divided by m probability of visiting that website, right? Because p of m is defined as the probability that when you go to a website at random, that you're going to be at website m. Okay, so p of so the user has a p of m probability of being at m, and then when he's at m, right? Well, m has a bunch of outgoing links. Okay, so for example, if this is our n over here, okay, and if this is m, right? So if I'm at this website, then I can go to any of one of my neighbors for the next website. Okay, I can either go to n, right, or I can go over here, right, or I can go over here. And the assumption is that this user who's currently at m, he's going to go to one of a random neighbor. Okay, so out of these three neighbors, he's going to pick one randomly. And so this is why we're going to take the probability that the user is at this website m, and then divide it by the degree of m, okay, because he's going to go to one of his neighbors randomly. Okay, so that is so this term right here is a probability that a user who's currently at m is going to come to n. Okay, but we have other neighbors of n also. Okay, so let's say that this guy is m1 over here. Well, we have other neighbors. So for example, m2. Okay, so if somebody is at m2, then so his probability of being at m2 is p of m2. Okay, and if he's at m2, then he's got he's got 4 neighbors that he can go to for his next website. Okay, and so his probability of coming to n is going to be p of m2 divided by 4, divided by the degree of m2. Okay, so that's what the second term represents. It's that when I'm not just visiting a random website, okay, then I'm going to be at a website m with this probability, and then from m, I'm going to come to n with the probability with this p of m divided by c of m probability. Okay, so Yeah. Okay. So this is how we're gonna. So what we want to do is to find these values p of n over here. Okay. Now, if you look at this, then you can see that these are. So if you think of these p of n's as like unknown values, okay, then what we're trying to do is solve for all of these unknown values. Okay. And in fact, here we actually have a linear equation. Okay, so because each of these p-values is an unknown variable, so if you write this out, then this becomes a set of linear equations that we're trying to solve. Okay, we have one variable, we have one unknown for each website, right? And we're trying to determine the probability of being at that website. Okay, so the way we can do that is, well, first of all, this system of linear equations is very large, okay, because we have like, billions of websites. Okay, so we're not going to apply any sort of direct method to try to solve this linear system. So for example, we're not going to do Gaussian elimination on this, okay, because that would be way, way too slow. So instead, we're going to use these iterative methods that we talked about. Okay, and one iterative method for solving these equations is just to start with some arbitrary values for these for the probability of being at different websites. Okay, so for example, you can start with a uniform distribution that I have the same probability of being at any website. And then you can just follow this equation and then compute and then iteratively refine these probability values. Okay, and then if you do this refinement process enough times, then eventually this is going to converge onto the actual PageRank values. Okay, so to give you, so to show you how this is being done, so suppose that in the initial iteration, we have, so we have 5 nodes over here, and initially the user's at one of these nodes randomly, so he's at each node with 20% probability, okay, with 0.2 probability. All right, now for each of these nodes, we're going to look at what is the probability I go to one of the neighbors of this node. Okay, so and this is going to be equal to the probability I'm at this node divided by my number of neighbors. Okay, so basically this term over here. So for example, this guy, right, he's got a 0.2 probability of being at N1, and then on the next iteration, right, he's got 2 neighbors, so there's a 0.1 probability he's going to go to N2, and then also 0.1 probability is going to go to N4. Okay. For this guy over here, right, he's got a 0.2 probability of being at N5. And for the next step, well, he's got 3 neighbors, right? He's got N2, N1, and N3. Okay, so he's going to go to one of them randomly. So the probability it goes to any one of his neighbors is going to be 0.2 divided by 3, which is 0.066. Okay? Yeah, so then this way we can form all of these probabilities that these various nodes are going to go to their neighbors. Okay? And then on the second iteration, the probability that you're going to be at a particular node is going to be the sum of all of these incoming probabilities. Okay, for example, over here, right, well, I've got a 0.1 probability that someone at N1 is going to go to N2. Okay, and there's also a 0.066 probability that somebody from N5 is going to come to N2. So therefore, the total probability that somebody is going to be at N2 is going to be 0.166. Okay, yeah. So you so basically you take the current probability, right? You divide it equally among all your outgoing edges, right? And then that way you have all of these weights being put onto these edges, and then each node is going to take all the incoming weights and then add them up, right? And that's going to be the probability for being at a node for the second iteration. And then for the second iteration, you're going to do the same thing. You're going to take your probabilities and divide it evenly among your neighbors, right? And then that's going to get you the probability for the third iteration. Okay, and then you just keep doing this. So you compute probabilities at each iteration, and eventually you hope that this is going to converge. Okay, and actually you can show that this does converge, and it actually converges pretty quickly. Okay, so to implement this in Mapreduce, what we're going to do is, okay, so for each node, n, okay, we're just going to look at, right? So for each node, capital N over here, we're going to look at how many neighbors it has. Okay, so that's the size of N's adjacency list, right? And then you're going to take N's current page rank and then divide it by its number of neighbors. Okay, so that's the amount of probability that N is going to send to each of its neighbors. Okay, and so next, for each of N's neighbors, we're actually going to emit one of these pairs where the key is going to be the neighbor's name, and then the value is going to be the probability that N is sending to this neighbor M. Okay, so then we emit a bunch of these key value pairs, and then for the reduce stage, what a node is going to do is to look at all of these incoming probabilities, okay, and then add them up. Okay, so for each of their neighbors, each of its neighbors is sending this node some amount of probability. Okay, and this node is just going to take all those and then add them up. Okay, so for so the probabilities that the neighbors are sending to this node M over here, okay, is going to be given by this list. So this node M is just going to add up all of the values in this list. And then that is going to be the new page rank for this node. Okay, and so that's one iteration of this PageRank algorithm using Mapreduce. And yeah, and it turns out that we have to do this for multiple iterations. Okay, so so in practice, so you can keep doing this until these probabilities don't change anymore. Okay, or you can just wait for the changes to become very small, and at that point your algorithm has converged. Okay. Also, you can just wait until the ranks between the nodes don't change. Okay, the ranks are like, who's got the highest probabilities. Okay, so for example, over here, right, the node with the highest probability, he's got the highest rank, right, and then this guy has second highest rank, third, and then what do we have, fourth, and then fifth. Okay, so you can also just keep running this algorithm until the ranks themselves don't change, even though the probabilities might still be changing. Okay, and it can be faster just to wait till the ranks don't change. So in practice, you don't have to run this for too many iterations. You might run this for, let's say, 50 to 100 iterations. Yeah, and then you can also use combiners with this, but this is only useful if if you have a mapper which yeah, if you have a mapper where there's a node that this mapper is processing a bunch of nodes, and many of these nodes point to the same node. Okay, in that case, if you use a combiner, you can combine all of the probabilities going to this node, right, from the other nodes on this mapper. You can combine all of those probabilities before you send them to the reducers. Okay, and then yeah, and then you can also try to partition the graph so that you get so that this behavior happens more often. Okay, and in fact, if you take a web graph, right, so these often form clusters, because, for example, if you look at all of Shanghai Tech's websites, right, they're going to point to each other with much higher probability than they're going to point to other universities' websites. Okay, so there's this cluster of Shanghai Tech websites, and there's this cluster of like Tsinghua websites, and so on. Okay, so when you have these cluster behaviors, then these combiners are going to be more useful. Okay, yeah. So this PageRank, we can run this in Mapreduce, and it's reasonably efficient. And since you don't have to run for that many iterations. Okay, so that's all we have for Mapreduce. Okay, so then talk to you guys later.